Ever since we've gathered into tribes, we've had the need to broadcast information to individuals within our groups. And in ancient times and in medieval times, governments did this with the help of town criers who got the latest updates on events that had occurred. And they went into the town square at a predetermined time and place to broadcast those events to the public. And then those listening to him were free agents. They could act on that information in any way they saw fit. And we'll see in a little bit that this is actually at the heart of event driven architectures. Similar to our requirements of event driven architectures or of technology in general, the town criers were chosen for certain attributes. So, for example, they would be chosen for something like an imposing presence or a booming voice. And to build resilience in that ancient broadcasting architecture technology, they put in laws in place to protect the town crier from any bodily harm. So an assault on the town crier was considered to be an assault on the person of the king himself, and as such was a treasonable offense. My name is Vijay Nadkarni, and I work as a solutions engineer at Confluent, where I talk to solutions architects on almost on a daily basis about event-driven architectures and how they're building an event-driven architecture at their companies and the lessons that they learn along the way. And as you can see, I love history. I love understanding the early origins of concepts and how these concepts evolve along the way, because I think this can help answer some key questions. Anyway, enough about history. We're here to talk about event-driven architectures. Naturally, the first question that comes up and that we have got to address is, what is an event? An event, very simply, is anything, any action that occurs in the real world that is worth capturing. So in the case of the town crier, it's any event that occurred that the town crier was, thought was worthy of capturing and then broadcasting to the public. We're going to ignore the use case, the obvious use case of propaganda in this discussion. In the case of event-driven architectures, an event is any action that occurs that has enough business significance to be captured and modeled in data that can be then shared between services. Now, this sounds like a very broad definition, but it's broad for a reason, which I'll come back to soon. An event, for example, just to give you some examples, an event could be a change in the stock price of or a change in the price of any security. It could be a cricket shot. So, for example, Virat Kohli hits a six. That can be an event that had occurred. For example, if it's a sports betting application, that would be an appropriate event to be captured. An event could be, somebody added, a user added an item to their shopping cart, and that could be an event, for example, at an e-commerce website. Or, if you're Nate Silver and you're building an election prediction model, a kind of poll of polls, then a single poll's outcome results could be an event. So how really is working with events different from synchronous API calls? Well, at this point, we know all about synchronous API calls. We know all about microservices. You've got a client and a server model where the downstream service, the server, offers to perform a task for the upstream service, the client. The server provides a function that the client can call on demand. So the server literally reacts to explicit service calls from the client. With event-driven architectures, this is flipped on its head in a few ways. First of all, event-driven architectures are a lot more data-centric compared to synchronous, microservice API communication, which tends to be more command-centric. I'll come back to that in more detail pretty quickly, but here's in a nutshell how that communication takes place in an event-driven architecture. You have a service that produces data that's captured in event. models it in data. It could be JSON, Avro, or something like that. And it publishes that data to a commonly understood medium, like a data streaming platform, like Apache Kafka, for example. I am most familiar with Apache Kafka, so that's probably the example I'm going to take the most. And it publishes it to a platform like that, and a consumer. Well, it doesn't have to be one consumer; it could be many consumers. Consumers can listen in on that platform and pick up the event data that is needed and act on it as they see fit. They are free agents, sort of like the people who are listening to the town crier in the town square. Now, this is clearly a big change from the way we think of microservices. First of all, consumers of data aren't acting on the explicit orders of the client or of the producer. Not only could they be built by a different team that did not build that built them, the producer. Not only can the implementation details of the consumer be unknown to the team that built the producer, but also the intent, or even for that matter, the existence of the consumer could be unknown to the team that built the producer. The raison d'etre of the consumer could be unknown. In theory, so these downstream consumers are clearly not acting on the explicit orders of the producer, and this is a huge change from the synchronous API communication that we saw with microservices. So now this brings us to why events are defined so broadly, because we don't always know who's listening in and who's picking up the event, or who will pick up the event in some time in the future. So it doesn't make sense to narrow down the definition of an event too prematurely. So why has this come about now? What has changed in the world that businesses are now adopting event-driven architectures? Well, very simply, it's cloud computing. The most compelling thing is cloud computing. And really, it's the fact that cloud computing has made data storage cheaper, it's made compute cheaper, and it's made network IO cheaper, which really has made it, has allowed services to communicate a lot more with all of the data that they collect and they have, share a lot more raw data between each other, share more processed data, and be able to reuse that data, whether it's raw or processed. But the fundamental question that we haven't addressed yet remains, why would we want to even adopt an event-driven architecture in the first place? So to do this, it helps to look at some of the drawbacks of synchronous microservice communication. First, you'll notice that that kind of communication requires a request response model. It has a request response model that makes services tightly coupled together. And sure, they're not as tightly coupled as they used to be when they were part of one big monolith. But they are still very strong dependencies here. Firstly, the client needs to know about the existence of the server. It needs to know its endpoint. So clearly, service discovery needs to happen. It needs to know its API, its data model. So basically, physical coupling exists between them. And then synchronous communication model also means that the client has to wait for the server to finish processing its request and sending its response before it can continue doing its work. Now, normally this would have been a blocking call in the client application, which would block the thread in the client, and it would block resources. And sure, we know ways to get around that. We can do this without blocking the thread, but the client is still waiting around for a response before it can continue doing its work. And this is temporal coupling. So we've seen physical coupling, and we're now seeing temporal coupling between these microservices. And all of this gets trickier still if these microservices are chained. And once you have a very complicated mesh of microservices, you're going to see chained microservices in this pattern. So service A calls service B, which then, in order to process service A's request, needs to call service C, which then calls service D, and so on. Now, if the last microservice fails, this leads to a cascading failure. Every service in the chain needs to be able to recover gracefully. So we're seeing some of the drawbacks already, right? Not only can this get chained pretty deeply, but like I said, if you have a very extensive mesh of microservices put together, you can also find a large fan out between these microservices. So for example, service C can call on 3 other microservices, X, Y, and Z, which can call on more beyond that. So this can make it quite difficult to trace what's happening where, and it can, this can blur the boundaries between microservices to some extent. So we've looked at resilience. Let's look at testing. So now you need to test these microservices, and to be able to do that, you also need to have all of the service that it depends on to also be functioning and operational. And that is a chicken and egg problem. And we can stub out the microservices here, like I've indicated, but that's good for basic stuff like unit testing. But for anything that's more extensive than that, this is clearly not sufficient. With services that are event-driven, they operate more independently, and they can be tested appropriately with appropriate production data that's existing on the data streaming platform. So you don't have to have downstream services that it depends on to be actually functioning. Let's have a look at scaling, because that's the next thing we do when we, after we've tested, we put them into production. Now we need to worry about, will these microservices scale to handle the loads in production? Now, synchronous microservices are supposed to scale independently to deal with high traffic volumes. But to think about what's really required here, to scale A, you need to scale out B as well. And to scale out B, you need to scale out C, and so on. And what you've got here is dependent scaling, which can get really, really tricky, especially if you've got very variable loads, very variable traffic volumes with surges, unpredictable traffic volumes. And this also now depends a lot on the technology that you use to implement and to deploy these microservices. Now, we've looked at dealing with resilience, we've looked at scaling, we've looked at testing. What happens next? Life changes, business priorities change, and we need to deal with that change, right? APIs evolve. That's how services deal with this change. A service now needs to continue serving clients that speak version 1 while now also speaking version 2 with another service. And this can get pretty complicated. The implementation details of service A can get quite complex. Now, overlap the chaining and the complexity grows even more. You can see that. With event-driven microservices, though, you manage change differently. Remember that they're communicating with event data. The schema for those event data can evolve, and there's ways to manage backward compatibility of the schema. So we've talked a lot about this. I think it's probably time now to talk a little more detail in a little more detail about event-driven architectures themselves. Now, there are a number of ways that we have seen event-driven architectures done. I think of them as existing on a spectrum of how much data or how much information is carried in the event messages. It's also a sort of a spectrum of boundaries and responsibilities between microservices. On one side is microservices with synchronous communication, which is over to the left. Then let's look at the event-driven architecture spectrum. First of all, we've got event notification, where producers simply notify other services about something that's changed. And so, for example, The notification could be a shopping cart updated or item added to shopping cart, but with no real details about what has actually happened to the shopping cart. So this has to be then followed by a synchronous API call to the event producer to get more information. Okay, so you said that that an item as was added to the shopping cart. What was that item? Give me more details. This is a hybrid, as you can see. There's still a lot of room for synchronous communication here that's triggered by event notification. The producer doesn't need to know the intent of the consumer, but it often does, and that event is almost purpose built. And it also it has a lot of all of the drawbacks of microservice communication. So we're not really getting rid of those. Let's move on to the next one. You've got delta events. These are events that carry just the delta, just the change in an object. So for example, the customer has 3 items in her shopping cart, and now she's added one more item in her shopping cart. So the event has the event notification, item added to shopping cart, but it also has the details of the item and the quantity that's been added to the shopping cart. This is a service that's consuming these has the delta, but in order to find out what items are really existing in the shopping cart, it needs to compute those. So this puts the onus on the listener to maintain event sourced state, right? This is really good if the event is internal to the domain that the listener belongs to, or that belongs to the listener. But if not, then this is risky. It's error prone. You're letting a service that does not own the domain calculate, aggregate up all of the delta events in order to calculate the latest state. And it's better to let this be done by the service that actually owns the domain that this object, the shopping cart, belongs to. That brings us to the next one on the spectrum. And this is one where the event message carries not just the event notification, but also has the latest state. So these are called state events. So they have the event notification. And so, for example, if the event is shopping cart updated, and it also has the latest shopping cart contents. The listeners to this now, the good thing is they don't have to compute the latest state. But if they do want to know what the difference is, what the delta was, then they need to compute that. So they would do this by doing a diff between the latest state and the previous state. They don't need to maintain event sourced state by aggregating up all of the past delta events. So that's good. They do have to maintain, they do have to store state in order to be able to diff it with the next state to calculate any deltas that are occurring. At least it's not sort of calculating state of an object that it doesn't belong to. So this can, this is good to be used with external events. And you can see where I'm going with this, right? You could even go further. You could say, we're going to get rid of this problem as well. We want to include in the event message, not just a notification and the latest state, but also the previous state, right? And what this does is now listeners have the notification, they have the latest state. And if they want to calculate the delta, they just diff that latest state with the previous state, both of which exist in the same event message. So it can compare the before and the after, which are both included in the same message. I just want to make one note on the language that we use about the events. So all of us developers know that naming things correctly is very, very crucial. So for example, with microservice communication, we know that we use HTTP methods like get and put and post and update and delete. And these are worded as commands. With event-driven architecture, it's important to stay away from that command terminology and to use past tense of verbs. So for example, events would be user logged in, or shopping cart updated, or item added to shopping cart. Um, so we've talked about how event-driven architectures are done. We've talked about why, what are the drawbacks um, of synchronous communication between microservices are, but I haven't talked a lot about some of the advantages of event-driven architectures. And it's important to note that, and I think I hinted at this before, that event-driven architectures are a lot more data-oriented or data-centric than synchronous communications, synchronous microservices communication, which tend to be more command-centric, right? Like I said, they have commands like get and put and post. Now, with event-driven architectures, what you're really doing is effectively taking out the data that would have been in the method of a response in a microservice communication response. You're freeing it of all of the commands. You're getting rid of the get and the put and the post, and putting all of them, not selectively, but all of them, onto a data streaming platform. Effectively, what this does is that you're freeing the data and letting it exist on its own, and therefore you're making it more of a first-class citizen. And what this means now is that you can not just have the data in order to communicate between producers and consumers, but you could also have stream processing frameworks like Apache Flink pick up the data from the data streaming platform and process those. You can use it to calculate aggregations and join and enrich data from different sources, different producers. You could do all kinds of things here, a lot more than that, all in real time, and put that output back into the data streaming platform, or you could have it spit that output into a data warehouse or a data lake, all in real time for further processing and analytics. And you don't have to wait to do it in batches with batch ETL tools. So these are some of the benefits of an event-driven architecture. Thank you for the opportunity for speaking at API Days. This has been great. Thank you very much. Bye-bye.